Thank you very much, Joachim. It's been a really great pleasure to be here for the last 2 days, or 36 hours, I think. And I spent today in the department talking with people. The department has an illustrious history, long and illustrious history with lots of famous people, famous professors, many of whom have contributed to the topics that I'm going to talk about tonight in very fundamental ways. So this is a mixed audience, and I'll admit that this is a challenge. I spent a lot of time talking to students and other scientists, so it's going to be a little bit more of a story of successes in science, and in particular, understanding the atmosphere, starting with predicting the future by understanding the atmosphere, and the successes that we've had over the years without having to worry too much about what's happening in the ocean. And so I'll spend some time talking about that, and then I'll move on to talk about where we are in terms of our present challenge, which is predicting the ocean and its impacts. So let me start by taking you back to a time when predicting the weather was just a fantasy. In the 1920s, Lewis Richardson was an English physicist and mathematician, and he hypothesized that it would be possible to take the laws of physics that apply to the atmosphere and predict the weather at some time in the future. And he was cleverly, and perhaps in a sci-fi fashion, was envisioning that this would actually be done by humans, individual humans. Each would represent a part of the globe and would sit in a stadium solving the laws of physics for that particular location. And then there would be someone in the middle that was conducting all of this. And so as a whole, they would be acting as what we now know as a modern-day computer. He called it the forecast factory. So a modern computer, but a very slow, very inefficient, and very inaccurate one. And he actually took the step to actually make the calculation for one particular place and made a 6-hour forecast. It took him 6 weeks with a slide rule, and then it was also wildly inaccurate. So fast forward to today, and now because we have global climate models, we have atmospheric observations from around the planet, we can make predictions with a great deal of skill 3, 5, 7, even 10 days out into the future. And this is just a recent forecast, actually nothing really that exciting for all you weather people, weather nerds I'll call them because I'm one, nothing really that exciting happening, maybe some extreme rainfall at some point in the central U.S. So the key to this prediction was knowing the atmospheric state very well, and that comes from a set of observations. But even knowing that very well, which gives us this predictability, we don't know it well enough to go beyond 10 days. So weather systems have this lifetime, and after a while, these inaccuracies in knowing what the atmosphere is doing now will actually compound over time and end up ruining the prediction. Now, we also use these same global models, or similar global models, to try to predict way out into the future. So this is a time history from 1850 to 2300 out in the future. So this is the historical period where we have observations. This is the next century and then 2 centuries out. And what we use these climate models for is to understand how the Earth's temperature is going to respond to changes in the atmospheric composition that are mainly caused by, in this case, entirely caused by human activity. And the outcome depends not on knowing the initial state of the atmosphere right now, nor does it really depend much on what the ocean does, but it really depends on something that's almost entirely unpredictable, which is humans. And it depends on what happens with the economy, and it depends on what decisions we make about how we produce energy. And that's shown here with the red lines showing extreme scenarios where we burn all the fossil fuels we have and until they're basically gone. And then you have blue scenario where we convert to renewables or non-carbon intensive energy sources. This actually scenario is almost impossible to get on at this point, the decisions we've made so far. So again, lots of understanding about the atmosphere from weather the next 10 days all the way out into the future. And now I want to show you a video which shows that this human-induced warming is already observable. This is a global map of surface temperatures from the 19th century through today. And what I first want you to see, no falling asleep, I know this is mesmerizing, but and I know it's late, and I know you've had wine, but I haven't, so bear with me. We have a fast forward this in time, and you see that there's a global warming. And starting back, I'll play this again, back in the late 19th century, was cooler than it is today, and the Earth warms over that time. But what I want you to also note is that embedded in that warming is a lot of what we'll call climate variability. So at any given region, the rate of warming can be much faster for a period of time than the global mean, or it could be slower. And this is the global climate change. The mean warming gets a lot of attention, but and this time scale I think has been overlooked. Now, what causes this variability? It's not greenhouse gases. Here, I'll play it one more time. It's not greenhouse gases, which are global in extent, and they vary more slowly than this. And you can see that the influence of greenhouse gases sort of by taking in the big picture and squinting over all these blobs and blobs of warm and cooling. And it's not the weather in the atmosphere, since weather systems move quickly and they only last for about a week or so. And this is where we turn to the ocean. So why? The ocean has a large heat capacity. We know this is easy to think about where you might want to go swimming, it's spring, but you know the water's still really cold even though the atmosphere and the land have heated up with the increasing sunlight. And that's because the ocean has a large heat capacity. It takes a long time for it to respond. And so it has a potential to store lots of heat and then return that to the atmosphere. And the other reason that we think that on this kind of intermediate time scale the ocean plays a role is because it moves slowly. So the fastest current, or one of the fastest currents in the world, the Gulf Stream, which is in my backyard, moves at an average rate of 4 miles per hour. So I could probably jog 4 miles per hour, but maybe not in these shoes. But the ocean has the ability to slowly pile up lots of heat in a particular region that can then impact the atmosphere and the weather in the weather of the atmosphere. So we think there are reasons to think that the ocean can matter in these intermediate timescales. And I will say that it's not just what's happening over the ocean, but it's how the ocean impacts the atmosphere that we're really interested in. And for example, we want to know what causes extended periods of droughts or extreme flooding, all of which you experience here in California and plenty of other places in the world. We want to know what causes things, what causes extended periods of strong hurricane activity. I'll come back to this in a bit. And this is where we think that the ocean can give us some ability to predict the future. Well, I'll say that's what the debate is. So here's an example where we know that the ocean has a big impact, and it's predictable. It has a predictable impact. So this is a picture of the surface temperature at the end of 2015 in December. This is a giant El Nino event. Who lived in California at that time? 2015, lots of you. Probably heard a lot about El Nino at the time. This is a picture of the difference from normal of the surface temperature, and you could see that it's about 5 degrees above normal over a quarter of the planet. This area represents practically a quarter of the planet. It doesn't look like that because of this map projection. 5 degrees above normal for an extended period of time. Now you can just imagine the amount of heat, the amount of heat that is available in that part of the ocean. And then fast forward to a year later, or a couple years later, and we have this extended La Nina period of time. So after the El Nino ends, the last El Nino end, we have this La Nina situation where the temperatures in this part of the world were several degrees cooler. I should note this is Celsius, so multiply it by almost 2 to get Fahrenheit. Several degrees cooler for not 1, but 2 years and counting. Now, in the 1980s, there was a mooring array that was set up in the tropical Pacific. Many people here were involved in the design of that and the implementation. And now we have this observations that we've maintained in order to have a picture of the ocean, not just what's happening at the surface, but down through the ocean depths. And this observational array has been instrumental, just like weather predictions, in providing us an estimate of the current ocean state, a good estimate of the current ocean state. So like weather, we can use that ocean state to make predictions about the future. But fortunately, in this situation, we actually can make those predictions not 7, 10 days out, but actually months, seasons, and even a year out. There are people that argue even multiple years out. This is a forecast from spring of the year of 2015, which was going into the big El Nino event that happened 6 months later. And you can see we have a collection of models from all over the world. This represents the work of possibly thousands of scientists over the years in building these models and building these observation systems in order to say, okay, we know what's happening now here in July, what will happen in the future, and then the observations are what we know happened, which was there was a big El Nino event. If we take this complete set of models, this was predictable. I will also note that I did my PhD at Columbia University. My PhD advisor, Mark Kane, who's developed one of the first forecast models for El Nino, made a forecast in 1986. People thought he was crazy. He was harshly criticized. He published a forecast. He got totally lucky. It was right, and his career was launched. Well, he'd already done a lot of really cool stuff by then, but he made a successful forecast, and he now says it's better to be lucky than good. So tropical Pacific Ocean drives the atmosphere. This is, as I mentioned, the amount of heat piled up in this region can then can heat up the atmosphere and change the storm track. So this is the position of the jet stream during an El Nino year, and you can see that the jet stream hits lower and hits this part of the United States all the way from Southern California to Florida, where I live. You expect, in general, on average, wetter conditions. Now, I hope somebody in the audience will ask, how come the last El Nino didn't end the California drought? And I think we'll come back to that. We have a panel of experts where we can spend some more time talking about that. This doesn't predict exactly what's going to happen. It's just how that average season will be. Now let's turn to La Nina conditions. The jet stream actually it hits the continent higher up, so you expect drier conditions across the whole southern U.S. So we're in a moderate La Nina situation right now, and as those of you reading the news about the Southwest or extended drought conditions in the Southwest U.S., in particular the Central Plains here in Oklahoma and Texas. And the red colors here show drought conditions. The deeper the red, the more exceptional or extreme the drought is. And there's exceptional drought across wide regions, but also there's drought conditions throughout a lot of the U.S. And this is a picture of the wildfires going on right now in Oklahoma and Texas. And I'm sure you're all familiar with this kind of situation. I was calling Alex to find out how the fires were affecting you, or the recent fires were affecting you here at the department. So this kind of change, persistent change in atmospheric circulation is caused by the ocean. We know La Nina changes where the jet stream hits the continent, and the consequences for the United States are pretty significant. I'll go one step further and say extended periods of drought have been observed in the past with major consequences as well. And everybody knows about the Dust Bowl of the 1930s. This was, there were 2.5 million people that left the Central Plains and migrated away, all kinds of environmental impacts that happened, all kinds of cultural events that this caused. But I should say that this started with a La Nina event, but it was exacerbated by two other things. One thing is the fact that there was a land use practices which made the topsoil very erodible, and so that caused the dust to be it caused the dust to have easy liftoff once conditions got dry enough there. There was another factor, which was that the Atlantic Ocean. And so here's the La Nina conditions you can see during that time period in 1938. And in the Atlantic, there were warmer than normal conditions in the tropical Atlantic. And we now know, thanks to the work of some of the members of our panel, Rong Fu in particular, that which I think we may hear about more, that influence of the Atlantic is also really important for U.S. rainfall. So let me transition into the Atlantic, my home ocean, beloved home ocean. This is a picture from the 18th century. It's credited to Ben Franklin, but I don't think he actually drew it. But he postulated that there was this strong current in the Atlantic Ocean. They knew this because the ships that were traveling back from Europe taking this route took twice the amount of time it took than going that route. So eventually they shifted the trade routes. But the beauty of that marine traffic that went back and forth across the Atlantic is that they were taking observations of surface temperature as they went back and forth. And the British government was collecting these global observations, and people have been going back and forth across this ocean for centuries. So now we have a long-term history of the Atlantic Ocean. And this is a picture of the average temperature of the North Atlantic Ocean going back to the mid-19th century. And I just take the average of this, and you can very obviously see, well, there's been a pretty significant warming since 1900 on. But on top of that, you see these cycles of surface temperature. There are extended periods of cold periods in the Atlantic, extended periods of warm period, a return to cold, and warming, about this overall warming trend. Now we know that changes in the Atlantic Ocean can impact U.S. drought, but I would be remiss if I came here from Miami and did not talk about something that people in Miami obsess about, which is hurricanes. This is a picture from September 8th of last year with Katia, Irma, and Jose. Irma caused the evacuation of 6 million Floridians. I was one of them, traveling with my mother-in-law. This was an extremely active year. We all know about the impacts that happened associated with Harvey, or even worse with Maria, that people in Puerto Rico are still dealing with. But one of the things that we know is that there are long-term cycles in hurricane activity. And this is a time history going back to 1950, and this is 2017 here, of the cycles in the Atlantic hurricanes. So you can see there are periods, very active periods, there are quiet periods. This period of time was actually when South Florida underwent an extreme population explosion. So it happened to be at a time when there was few hurricanes, which is a bit unfortunate for planning-wise. So you can see 2017 was a very active year, but there have been other active years as well. You can see by eye these cycles. Now, if I put on top of this the temperature, you see there are long-term, they coincide with these cycles. And it makes sense physically. We know that warm temperatures in the Atlantic fuel hurricanes. When we make seasonal forecasts, we say, okay, if the Atlantic is warmer than normal, we can expect it's not the only predictor. There are other things going on, but it is an important predictor of hurricanes in addition to cycles and drought. Now, what causes these long-term cycles? This is a video. It's a cartoon of the ocean circulation in the Atlantic, which is unique among the world's oceans in that there is a flow from the southern hemisphere into the North Atlantic that brings heat with it. So what you can see, these arrows are depicting a kind of a cartoon version of the ocean where there's warm water coming in at the surface, makes it all the way up to the Nordic Sea, or to the Greenland-Iceland Sea. It sinks and comes over the ridges and flows out as cold water. Bringing warm water in, exporting cold water is a net import of heat. So this large-scale circulation is bringing heat into the North Atlantic. And the idea is that if the circulation were to speed up, it would heat up the North Atlantic, cause more hurricanes, cause more drought in the Great Plains. And if it were to slow down, then it would make the Atlantic colder. So that's an interesting story. Does anybody want to watch this again, or are you satisfied? All right, no hands going up. So that's one school of thought. Now, my colleagues at the University of Miami and partners in Europe have spent a lot of time constructing an observational network to measure this circulation. There's an array of moorings that are moored to the bottom all the way across from Africa to off the coast of the Bahamas here, and they're now able to measure this overturning circulation. They have been doing it since 2004, though, so you don't really have a picture of these long-term cycles and how they are affected by this overturning circulation. But what do we know about the overturning circulation? Their measurements shown here in red since 2004 is that the circulation has been weakening. So the implication here is that the North Atlantic, a weaker circulation will be bringing in less heat, and the North Atlantic will be cooler. That would be good news for hurricanes and for drought in the U.S. But there is another school of thought, and this I'm going to take a little bit of time to talk about my own research, and I gave a lecture on this at the department yesterday. There's another school of thought of what causes these long-term cycles, and this is where the debate is, that we've been arguing that the ocean is not playing a primary role in that. And let me show you, give you a bit of a view into what I do as a climate modeler. Jochen mentioned that I use climate models. This is a picture of the warm period in the North Atlantic Ocean. You can see the ocean is warm throughout. Overlaid on that are the winds. The atmosphere is also changing as well. If you take a climate model and you say, can you produce these kind of warm periods, they do a pretty good job. So a climate model that has a dynamic ocean, so it has this overturning ocean circulation, and it does a pretty good job of representing reality. Okay, so seems to work. This idea seems to work. Well, the fly in the ointment is that if you take a climate model with an ocean that does not move and look at the same, and look for periods of warm and cold in the Atlantic, you get the exact same thing. So in our climate models, though they have an ocean that moves, they do not, from our work has shown that they do not, that changing ocean circulation doesn't seem to be necessary in order to explain these warming and cooling periods in the Atlantic Ocean. So what is causing them? And this is, I think, one of my last pictures, so I'll permit myself a little bit of how are we doing on time? Okay. So this is mostly some results with the climate model. So what you see in what you see in the red is the time history, the observed time history of the Atlantic with these long-term cycles. And then in gray, you see a bunch of gray wiggly lines. And the point is that you can see they're all kind of doing the same thing. So we have a period of time with where all these gray lines are going down. It's the same time the observations are going down, and then a sort of steady swing up at the end. And what this is, what the gray lines are showing you is when you take a climate model and you change the composition of the atmosphere in a way that we know happened in the past, and so we have increasing greenhouse gases at the end, but in this period of time, we actually have an increase in the amount of soot in the atmosphere due to the post-World War II industrialization of Europe and North America, which put a lot of soot into the atmosphere and actually cooled the North Atlantic Ocean at that period of time. And so our climate models show that this kind of cycle is not actually a cycle. It's actually just the ocean responding to the atmosphere and changes in the atmospheric composition, which have these long time scales, and are a factor of things, decisions we make about how we burn, how we produce energy. So this has the, if we want to extrapolate in the future, I have a question mark here. Does this mean warming is going to continue into the future as we increase greenhouse gases, which means more hurricanes and more drought? And so I will leave it on this note to say there's currently a debate about this, and it's been an ongoing debate for several years, and we're still working on the answers. So let me wrap up with by trying to provide an answer to this question: does the ocean matter for predicting the future climate? So El Nino and La Nina have taught us that the answer to this question is yes, that we can predict events 9 to 12 months in advance, and we know what their impacts are in the atmosphere, so we know what to be expecting several seasons out in advance. But clearly, there is significant seasonal and decadal variability in the ocean outside the tropical Pacific, and that affects the climate as well. So the example that I give here, when you talk about, there's a real debate about whether you need an ocean circulation dynamics in order to understand and predict this variability, and the Atlantic is my example on that. So what I would say is that we're just starting to get a more complete view of the ocean's rich variability, and so this is This is a picture of NASA's simulation of the global ocean with a high resolution ocean model. And it's really to give you a sense of, I've talked about particular regions of the ocean. I've talked about a lot about the surface of the ocean, which is fairly well observed. I know there's JPL people here who spend their lives building satellites that can see the global ocean. But we have very little understanding of what's happening beneath the surface. I read a quote recently by a famous oceanographer that said, less than half of the ocean, of the volume of the ocean, has ever had even one instrumental observation in it. Even one. So trying to figure out how things are varying with time is a daunting task. But if we think back to Richardson in the 1920s and hypothesizing about what is possible in terms of our understanding, we may be at that stage with this problem of predicting the future of the ocean and its consequences for us on land. So with that, I will turn it back over to our moderator and the panel. Thank you.